So this section is section 4, and it's called special products. Now these are special because they have like a pattern, or they just, it just looks like something. If you ask me, everything that we're going to be doing here is going to be the same exact thing of what we're used to. So before we do an example from this section, I want you to explain this to me. Remember, 5 to the second. That means 5 times 5. Do we all remember that? So if you think about this, I can give you a problem like this now. Now this is what we call a special product. This is read the quantity of x plus 5 to the second power. Now, if you're sitting there thinking to yourself, oh, that's easy, Float. I can do that in my head. The answer's x squared plus 25. I would say you're wrong, because that's not what this is. You got to remember the definition of an exponent. The quantity x plus 5 to the second power means the quantity x plus 5 times x plus 5. Now, we have to apply the distributive property. So I'm going to underline the x, draw my arrows. X times x is x squared. X times 5 is 5x. Now that I distributed the letter x, I'm going to go ahead and distribute the positive 5. 5 times x is plus 5x. I write it directly underneath. And 5 times 5 is 25. So now, when I combine these together, I get x squared plus 10x plus 25. And that is what the quantity x plus 5 to the second power is. In other words, what we had to do first was write it out. You got to write it out. Now, I do feel bad for those of us who had a bad math teacher in the past. When I was in your shoes on the other side of the desk learning this stuff, one of my professors, Dr. Williams, asked me, he goes, Float, would you like to be a tutor? You can make some money. I was like, yeah, sure, I'll tutor. So I worked in the math lab down at California University of Pennsylvania. That's what I did when I was a student. And I had one student who always came to me for help. And this student was a math major, wanted to be a math teacher, and could never, ever get this problem right. And the whole time I'm sitting there thinking, ugh, and you want to teach math. I'm going to get your students one day and they're going to get this wrong every single time. So, please, take the extra 30 seconds and write it out. Okay? Here's a problem for you to do. The quantity x plus 3 to the second power. Please do that. Okay. So, what would be my first step here? Anybody? Write it out. Very good. So we have the quantity x plus 3 times the quantity x plus 3. Now we distribute. X times x is x squared. X times 3 is plus 3x. Hallie, am I doing this right? Okay. Now I underlined a 3, and I distribute it. Dawn, what's 3 times x? 3x. Good. You're muted, but I could read lips, so we're okay. And what's, anybody, what's 3 times 3?
9.
Perfect, Wesley. Everything's already organized. It's grouped in like terms. I just go right down the columns. X squared plus 6x plus 9. Okay? Now, what makes this really special, and I'm going to zoom out so we can see both problems here. What makes this really special is right here. If you look at both situations here, try to maximize this as much as I can. If you look at that 5, ask yourself a question. What's 5 plus 5? 10? Oh, come on, floater. So 5 plus 5 is 10. And what's 5 times 5?
25.
Everybody see that? You see the pattern? Look at the second problem. What's 3 plus 3? 6. And what's 3 times 3? 9. And here's what makes this so special, okay? These are called binomial squares. Write it in red. All right? And what we just looked at was this situation right here. When you have two things that are being added inside of parentheses, and then that entire thing is squared. First, you know to rewrite it. Okay? And if you were to distribute this and group all your like terms, you would end up with this as an answer. A squared plus 2ab plus b squared. So let me show you that. Remember, a times a is a squared. A times b is plus ab. Now we're going to distribute the b. B times a is the same thing as a times b. And b times b is b squared. So when you add these together, you get a squared 2ab plus b squared. Does that make sense, everyone? In a way, if you can recognize this, you can save yourself some time. So directly underneath, I'm going to write the quantity of 2x plus 7 squared. Now, like I said, if you can recognize this, you can save yourself some time. So how about this? Everyone just watch. Just put the pencils down and just watch for a second. Notice this has the same exact form as the binomial square written in red. Okay? Which means wherever I see a letter A in my formula down below, wherever I see the letter A, I'm going to write 2x. And wherever I see the letter B, I'm going to write a 7. Does that make sense, everyone? So watch what I do. First, you know me, I like to put parentheses before I substitute. Now, wherever I see the letter A, I'm going to write 2x. Wherever I see the letter B, I'm going to write a 7. So the only thing I have to do now is just simplify. The quantity, 2x to the second power, is going to be 4x squared plus 2 times 2 is 4. 4 times 7 is 28x plus 7 to the second power is 49. So you can save yourself some time if you can recognize that you have this binomial square. However, if you don't recognize it, you can still do it the old distributive property way that I really like, and you're going to get the same answer anyways. Does that make sense? Now, there is another binomial square that I want to introduce us to, and it's this one right here. Notice the only difference is there's a minus sign instead of a plus sign. So if we were to write this out, all right, what you would get if you were to distribute everything would be a squared minus 2ab plus b squared. Okay? I will be honest with you. I'm going to be fully transparent. If you don't memorize these, I don't care. I really don't. I'd rather you know how to do the problem. I'd rather you know how to do it than just memorize a formula. Okay? So we might as well do an example where we got to subtract. So how about this? Give me 1 second. I'm going to use the power of technology. All right. Here's the example we're going to do. 4x minus the quantity 4x minus 5y to the second power. And I'm going to do it both ways. Old school way and then new school formula way. So old school way first. The quantity 4x minus 5y squared means the quantity of 4x minus 5y times the quantity of 4x minus 5y. Okay? So now I just use my distributive property. 4x times 4x is going to be 16x squared. 4x times negative 5y is going to be minus 20xy. Now, I switch gears and I distribute the negative 5. Negative 5y times 4x is going to be negative 20xy. Again, I just put them in order. And then negative 5y times negative 5y is going to be positive 25y to the second. When we group everything together, we're going to get 16x squared minus 40 times x times y plus 25y squared. Are there any questions with that? Dylan, you good?
Yes, sir.
All right. So that was the old school way. That was the, man, we're just gonna brute force this. Here's the new school. This is the formula. So above, A is going to equal 4x and B equals negative 5y. So I'll zoom out here a little bit just so we can see the formula. All right. And then what I'm going to do first is just write, oops, sorry. I'll write the result of my formula here. And wherever I see the letter A, I'm going to write 4x. Wherever I see the letter B, I'm going to write negative 5y. So, before I do anything, I put parentheses first, and then I make my substitution. 4x and 4x, and then negative 5y and negative 5y. Now I simplify. The quantity 4x to the second power is 16x squared. What's going on here? Oh, I made a mistake. You only want the 5y. See, this is why I hate using formulas, because I make mistakes all the time. You don't want to include the sign in front of the number. You just want 5y. That's it. Okay? Now, in the middle, you get negative 2 times 4, which is negative 8. And then negative 8 times 5 is negative 40 xy. And then lastly, on the far right, the quantity 5y to the second power is 25y squared. So notice you get the same exact thing. I don't care how you do it. Whatever you prefer is what you go with. If you're asking for my advice, I'm old school. That's me. Are there any questions so far? Leah, did you dye your hair? It looks darker. Oh, you don't have any lights on in your house. Okay. All right. Now, here's the next special product. And this is personally my favorite. Megan H., this is my favorite. Okay? Does anybody know what those are called? They have a special name. Now, I want you to look at the problem first. You got the quantity x plus 2, and then you have the quantity x minus 2. So, I'm going to just preface this right now. I've been teaching this class for a long time. I've only had one person get it right so far. Does anybody know what these are called? Who can be the next person to get it right? Austin, you have your hand up. Do you know what they're called?
I've learned about these before. I think they're called perfect squares.
They are not perfect squares. What you're thinking of is the answer, where x squared is a perfect square and 4 is a perfect square because 2 to the second power is 4. But you're close, Austin. Anybody else want to take a guess while I eat part of my pumpkin cookie with pumpkin icing? Now I will take a drink of Trainer's iced tea while you're thinking. Going once? Yeah, they're not Punnett squares. Get biology out of my classroom. They are called conjugate pairs. If you can remember the word conjugate pairs, your life in math is going to be really easy, because they come up a lot, and you're going to be one of the few people that actually knows what they are. And here's what a conjugate pair looks like. Conjugate pairs will always have the same terms inside of the binomials. The only difference are the signs in the middle. And what makes these so special is that when you distribute, you're going to get x times x, which is x squared. X times negative 2 is minus 2x. Then we underline a 2 when we distribute that, so we're going to get plus 2x and then minus 4. And what you're going to notice is every single time when you multiply conjugate pairs, the middle terms always cancel themselves out. always. So the key is just to be able to recognize that you have conjugate pairs. And if you can do that, life is easy. All right? So here's an example here. Draw like a little line. Ask yourself, are they conjugate pairs? Yes or no? Leah says yes. Okay. Brendan, why are they conjugate pairs?
Because one pair is x plus 4 and the other is x minus 4.
Perfect. Same terms, signs are opposite. As soon as you know that, you can save yourself a lot of work, Sydney. All you have to do is multiply x times x and then positive 4 times negative 4. You don't have to worry about doing all the distributive stuff because as soon as you recognize conjugate pairs, we know those middle terms will always cancel themselves out. So you can save yourself a lot of work. I will guarantee you this. You're going to see conjugate pairs a lot, especially in this class. Because number one, they're really easy to recognize. And number two, they're really easy to simplify. And when we get into chapter 7, which is factoring, tons of conjugate pairs. Because they're really easy to factor, which is a technique that we're going to learn later on. Dawn, do you have a question?
Yeah, make sure you give me a lot of them on the test.
I will. I'm telling you, I do. I give a lot because they're easy. All right, let's try another one here. Are they conjugate pairs, yes or no? Wesley, what do you think?
Yes.
I agree. So do I have to worry about multiplying everything or can I be a little selective now? All right, so what's 3x times 3x?
9x squared.
Perfect. What is negative 1 times positive 1?
Negative 1.
That's your answer right there. All right. Are there any questions with this? Well, I do have a question for you. I'm going to write the previous problem on the board. Now, both examples here were conjugate pairs. I'll write out the answer as well. They're both conjugate pairs. What do you notice that's different about them? I'll give you a hint. I'm talking about location. Perfect. So Leah is kind of quiet today. Microphone's not picking up good. So I'm just going to repeat what Leah said because 100% correct. In the first example, notice that the negative sign was first and the positive sign was second. However, in the second example, the positive sign is first and the negative sign is second. Doesn't matter which one's first and which one's second. Not at all. The only thing that matters, are they conjugate pairs? Because if they're conjugate pairs, you can save yourself a lot of time. Let's look at this one. Notice here the variable is actually second. But it doesn't matter because we have conjugate pairs. Same terms, opposite signs in the middle. So 9 times 9 is 81. And negative 2y times positive 2y is going to be negative 4y to the second power. All right? All we got to do is just be able to recognize that we have conjugate pairs. So here's the most complicated one I can give you at the end of the day. Megan D, are you ready for this? Because it's going to be tough. Here we go. There you go. I'll give you a minute. Write it down. And then tell me what you got.
I actually have a quick question.
Go ahead, Wesley.
Can we reorganize it to where it's minus 4y squared plus 81, or will we just leave it like that?
So are you asking me, can you do this? Is that what you're asking me?
Yeah.
Yeah, 100% you can do that.
Cool.
Yeah. All you're doing is just writing it in the opposite order. That's fine. Sydney, did you just wake up? I keep seeing like yawning, like rubbing your eyes. Like maybe you just woke up. All right. So Sydney, help us out then. What's the answer? Okay. Well, let's think about this. You ready? We know they're conjugate pairs. So all I have to do is multiply those together. All right? So what's 1/3 times 1/3?
1/9.
And what's y to the third times y to the third? Remember, bases are the same, so what do you do with the exponents when you're multiplying? I'm sorry, say that again?
Add them.
Yep. So what's 3 plus 3?
6.
Good. So the first term is 1/9 y to the 6th. Now, a negative times a positive is a negative. What's 2 times 2?
2 times 2 is 4, so -4.
And what's x times x?
X to the second.
And that's it. So although this conjugate pair looked extremely complex because you got different variables, you got exponents, and you got fractions, did the technique change? Not at all. All right? So I was, excuse me, I was talking to a student the other day. I forget who it was, but I said, I want you to ask me a question in class. And I can't remember if it was this class or if it was another class. But here's the question I wanted the student to ask me, which was, Mr. Float, if you were to study for this test in Chapter 6, how would you study? Because no one's ever asked me that before. Students always ask me what's going to be on the test, but nobody's ever said, put yourself in my shoes. How would you prepare for this coming up? This is how I would prepare. I would understand conjugate pairs. I would understand that when you have conjugate pairs, that the form is going to look like this. And I would know that if that's the form, my answer will always be this. Now, I don't know how many of us read our book. Okay? But if I just drag this over and maximize it, right here, it says the product of conjugates pattern. And as you can see here on the left-hand side, we have a minus b quantity times the quantity of a plus b equals a squared minus b squared. Okay? And notice they give you like a roadmap. They say if you have conjugates, which is right here, sorry, I can't really highlight it, but that's going to equal a squared minus b squared. That's what I would know. That's what I would study. In fact, if I scroll up a little bit more, they define what conjugate pairs are. And then, sorry, I'm going the opposite way. Let me see. Bunch of examples. They give you tons of examples here. They summarize everything for me in a nice table right here. So if you're asking me how would I study for the test, these two columns is what I would know. On the front of a note card, I would have the words binomial squares. And then I would have a plus b, quantity to the second power, and then the quantity a minus b on the second power. On the back of the note card, I would have the whole thing written out. And I would understand that. Same thing with the conjugates. On the front of the note card, I would put product of conjugates. Underneath that, quantity a minus b, a plus b. On the back, I would write the a squared minus b squared thing. If you think about what I test you on, how many times do I give the same exact problem that I did in the homework or in lecture on the test? Amy, how many times do you think that happens?
Often.
The same exact problems? I just recycle them?
Similar problems.
Similar problems, but are they the same? They're never the same. However, the technique is. The technique is. So, this is, I mean, I am not like, inventing new math or anything. This is legit section 6.4 special products. All right? If you go back to section 6.3, anywhere where it says this. So let me scroll down because I want to see something real quick. Please excuse my dear Aunt Sally because I'm looking for something very specific here. And it's right here. Oh, I hate that one. Anywhere where you see this stuff right here, like multiplying a trinomial by a binomial, what does it say? To multiply a trinomial by a binomial, use the distributive property and the vertical method, which we know as the vertical addition method. It's all there. If you're asking me what I would study, I study the definitions. I don't study specific problems. I use the problems to further my understanding of the definition. But that's how you got to study math. Remember, I told you I'm going to teach you how to study math. That is how you do it. You study the definition, conjugate pairs. Quantity A plus B, quantity A minus B being multiplied. It's your job to be able to recognize that. Okay? Megan H, are we good? You sure? You think so? You're muted there, but don't worry. I'm getting really good at reading lips. You should see how many times Wesley makes fun of me. All right. I'm just kidding, Wesley. You've never said anything mean.
You weren't supposed to say anything.
So, we're done with section 6.4, which is special products. Now we're going to move into section 6.5. Section 5. Now, section 5 is called Divding Monomials, or just divide monomials. All right. So, in order for us to do this, we're going to have to look at some new rules, okay? So, we already have 3 rules under our belt. We have the product rule, we have the power rule, and then we have the product of a power rule. So now what we're going to do, excuse me, is we're going to look at the quotient rule. But here's what I want to ask you real fast. me see. Who's feeling pretty smart today? Let me see here. I'm gonna call on somebody. I'm gonna go back to Amy. Amy, can I ask you a question?
Yeah.
Do you know what 5 to the 0 equals by chance?
1.
How did you know that?
I forget the reason, but I remember learning it.
I agree with you. 5 to the 0 power is 1. In fact, that's a really special rule that we're going to learn. It's called the zero exponent rule. Okay? Amy, can I ask you another question?
Yeah.
What's 25 divided by 5?
5.
Now, a long time ago, in a galaxy far, far away, here's what you did. Now, you might not remember this, but here's what you did. You took that 25 and you said, I'm going to break that 25 down. We all know that 25 times 25 is 5 times 5. Then, you have a 5 in a denominator. And what Amy recognized so quickly, you didn't even know you did this, is that you have a 5 in a numerator and a 5 in a denominator, so you just reduce them. They turn into a 1, and that is how you got the answer 5. There's a much easier way to do this, and it's called the quotient rule. So let me show you what the quotient rule is. The quotient rule says this. If A, comma B are numbers, and B does not equal 0. Actually, no, I don't want to say that. Let's say it like this. I'm giving you the wrong definition already. So if A is a real number and A does not equal 0, because that's really important, and M and N are, and we're going to call them whole numbers for now, then if you have two exponents and you're dividing and the bases are the same, all you have to do is subtract the exponents. All right? Now your book gives you this really crazy looking rule. All right? So I just broke it down into basic language here. Now, let me show you what I mean. Here's a really easy example. 5 to the second divided by 5 to the first. Now, we know 5 to the second is 25. And Amy told us earlier that 25 divided by 5 is 5. Here's another way of doing this using exponents. Notice the number 5, the bases are the same. So all I have to do is subtract the exponents. Last time I checked, 2 minus 1 is 1. So 5 to the second divided by 5 to the first is 5 to the first, or simply just 5. Does that make sense, everyone? Now, where this rule really helps us is when we're dealing with exponents. Because here's the thing. When we're dealing with variables. Because here's the thing. We have no idea what x is. So in this situation, before you walked into this class, and before I told you about the quotient rule, the only way you could have done this problem is like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You would have had to write 10 x's in a numerator, and then 3 x's in a denominator, and then you would reduce 3 x's and you would count how many were left over. That's the only way you could have done this problem. However, now you know the quotient rule. And the quotient rule says that if the bases are the same, all you have to do is subtract the exponents. Much easier and a very fast way of simplifying things. Are there any questions so far? Are we sure? All right. The only way I can make these problems more difficult for us is if I give you something like this. Notice here, I'm giving you coefficients out front, but we should know how to deal with them. What's 8 divided by 2?
4.
Now, x to the 4th divided by x to the 3rd. Subtract the exponents. 4 minus 3 is 1. Are there any questions so far? All right, now there is one thing I do want to show you. In every example that we've done so far, and I will highlight. In every example that we've done so far, we're always dividing by a monomial, okay? This is the technique on how you do this. If you have like a binomial or a trinomial in the denominator, things get different. In fact, that is section 6. So in this entire first section, we're always going to be dividing by a monomial. Okay? Does that make sense? Now, there may come a time where you have something crazy like this. Now, I don't know about you, but I do not want to get my calculator out and type in 10 to the 15th power. Does anybody know how large that is? It's huge. It's a massive number. But here's what I know, Leah. If I have 10 to the 15th divided by 10 to the 13th, I know the bases are the same, which means I subtract the exponents. 15 minus 13 is 2. So the answer is 10 to the 2nd power, or 10 times 10 is 100. All right, how are we looking so far, everyone? Are we okay? All right. Now we're going to come back. I think we're going to come back to Amy, because Amy helped us out with this one earlier. I keep using X. Well, let's use the letter A for Amy. A to the 5th divided by A to the 5th. Now, according to the quotient rule, the bases are the same, which means we subtract the exponents. However, 5 minus 5 is 0. And Amy, what is A to the 0 power again?
1.
Perfect. The answer is 1. All right? So now, excuse me, I'm going to take a drink. I think it's really good to understand why. Okay? So the first thing I'm going to do is write out what the rule is. So here's your next rule. It is called the 0 exponent rule. This would definitely be a flashcard, by the way. So the 0 exponent rule basically says this. Basically, any number, any number raised to the 0 power equals 1, except 0 to the 0 power. 0 to the 0 power is undefined. It's one of those weird ones. So 4 to the 0 equals 1. 8 to the 0 equals 1. Even pi to the 0 power equals 1. Okay? But I think it's really good if we understand why. So earlier I gave us this problem, and now I'm going to kind of drag it out here a little bit. 5 to the third divided by 5 to the first is 5 to the 3 minus 1, which is 5 to the second, or 25. Okay? Now, if we write out this problem, though, what we would have would be 5, or I'm sorry, we would have 3 number 5s in the numerator, and then 1 5 in the denominator. And what you would do is just simplify. So you're left over with 5 times 5, which is 25. Then I said, all right, well, 5 to the second divided by 5. We wrote this out. Reduced. And notice that the answer was 5. How are we looking so far, everybody? Pretty good. Do you see a pattern starting to develop, Megan H? Here's the last one. According to our zero exponent rule and the quotient rule, 5 to the first divided by 5 to the first would be 5 to the 1 minus 1, which is 5 to the 0. And according to our rule, that equals 1. And here, the answer is staring us in the face. If I saw you in a grocery store, all right, and I asked you to explain fractions to me, how would you explain the fraction 5 over 5 to me? How would you explain this right here in the lower left-hand corner of your screen?
Goes into 5 one time.
Okay, that's good, but what if I don't know division? So all I'm asking Wesley is just for another way to do it. You're correct. 5 goes into 5 once. What else? What is this? What is this called? What is that called?
Numerator.
Good. What is this called?
Denominator.
Good. So if I were to draw this fraction, the denominator tells me how many pieces I need. The numerator tells me how many I shade. 1, 2, 3, 4, 5. Notice I shaded the entire rectangle, correct? Another way we can talk about the numerator, that's the number of parts that you have. The denominator is the whole. If the parts equal the whole, you have one whole object, whatever that is. Does that make sense, everyone? So now, instead of just memorizing, oh, anything to the 0 power is 1, what you're really doing is you're just drawing a fraction where you're shading everything in. One whole object. Does that make sense, everyone? All right. So we're going to do one more thing today. We're going to learn one more rule, and then we're going to call it a day. So here's an example right here. X to the 5th divided by x to the 8th. Notice bases are the same. So I'm still going to go ahead and do my thing, which is the quotient rule. However, Austin, what's 5 minus 8?
-3.
And here's where we run into the last rule. All right? We don't like negative exponents. We just don't like them. So the last rule that we're going to learn is called the negative exponent rule. Sometimes, depending on how old the professor is, and what I mean by that is the only person I ever heard talk or give it this name was like 4,000 years old. I think they were there when they created the rule. It's called the reciprocal rule, and you're going to see why. The negative exponent rule says this. If you have a negative exponent, you can rewrite it as a positive exponent by making it into a fraction, putting the base and the exponent in the denominator, but writing the exponent as a positive number. Now, it's called the reciprocal rule because if you look, I can make any whole number, or I can make anything a fraction just by putting it over 1. And if I reciprocate it, which means flip it, now it turns positive. Does that make sense, everyone? Now, if we go back up to this problem up above, the x to the 5th divided by x to the 8th, visually, here's what's happening. X to the 5th means I have 5 x's in the numerator. X to the 8th means I have 8 x's in the denominator. So if I were to write them out and simplify, notice these reduce. All 5 of these x's reduce. And look what's left over. 3 x's, but where are they? Are they in the numerator or denominator?
Denominator.
Good. So if I were to take my result, x to the 3rd, I'm sorry, x to the negative 3, and I were to apply my negative exponent rule, what I would have to do is rewrite it as 1 over x to the 3rd, which is exactly what that picture is showing us right there. Does that make sense, everyone? All right. So before we leave, what I want to do is just create a big summary of all the rules we've learned. And then when we come back on Friday, we're just going to pick up where we left off. So here's our summary of rules. First one is the product rule. And that's a to the m times a to the n equals a to the m plus n. You add the exponents. So that's our first rule. Second rule. Is our power rule. That one says, if you have an exponent raised to another exponent, you multiply the exponents together. 3. We had our power of a product. And that rule said this. It basically just said if you have things that are being multiplied inside a quantity, I don't care what the exponents are, what we do is we multiply all the exponents together. So a to the np times b to the np. Today, we added our quotient rule. And you're going to notice something here. Now that we're getting really hardcore into this quotient rule, I'm going to start putting those exponents inside of boxes. You will see why. Just for now, believe me. Our fifth rule, zero exponent rule. Anything to the 0 power is 1 as long as a doesn't equal 0. And then our last rule is going to be the negative exponent rule. And that is a to the negative m equals 1 over a to the positive m. So, If you were to ask me, Mr. Flo, what would you really study for the test that eventually is going to come up? If you were a student, how would you prepare? I would have those 6 rules memorized. You never really hear me say memorize things in math. Understand how to apply these 6 rules. If you could do that, there's no reason why you couldn't go on to Calc 1, Calc 2, Calc 3, linear algebra, quantitative mathematics, numerical mathematics, all that stuff. All right? So I'm going to call it a day. That's it for me.